Previously, I showed you how we can perform hypothesis tests on comparison of means when the variance is known, and here I'm going to talk about the case when variance is unknown. So when variances were known, we saw that there are 4 cases. Variances are equal or unequal, and each of those with sample sizes equal or unequal. And we saw that you can follow this chart here to determine the test statistic that you need to compare to the standard normal distribution. Now we're going to consider the variance unknown case. Similar to the variance known, we're going to have variance equal or variance is unequal, sample sizes equal or unequal. And again, you're going to learn in subsequent screencasts how to determine if the variances are equal or unequal. There's actually another test based upon the F distribution. So let's take a look at when the variance is unknown, and this is the more common situation. When sample sizes are small, variances are unknown, we have to use these methods. Here, we must estimate the variances from the samples and have to treat 2 cases. Do the 2 samples come from populations that have approximately the same variances, or do those 2 samples come from 2 populations that do not have the same variances? If we assume that the samples come from 2 populations with the same variances, the variance of the difference between 2 means, it can be shown, is sigma squared times 1 over n1 plus 1 over n2. We use a pooled estimator. This is essentially a weighted average. We subtract 1 from the 2 sample sizes, and we divide by n1 plus n2 minus 2. This just accounts for the reduced degrees of freedom that we are using because we're using up a degree of freedom to calculate x1 bar and another degree of freedom to calculate x2 bar. So we pool this, we calculate a pooled estimator SP squared. We calculate our test statistic. Our test statistic is similar to what we've been doing in the past. Oftentimes the difference in means is going to be equal to 0. Now in this case, we divide by our pooled standard deviation times the square root of 1 over n1 plus 1 over n2, and we compare this to the t-distribution with n1 plus n2 minus 2 degrees of freedom. For example, if we're doing an upper-tailed test, our null hypothesis is the means are the same. Our alternate hypothesis, mu1 is greater than mu2. We calculate a test statistic. Again, we're assuming that the variances are unknown but equal. We compare our test statistic to T alpha with n1 plus n2 minus 2 degrees of freedom. For an upper tail test, if this is true, if our test statistic is greater than T alpha, then we're up in the upper tail, which is rare. If the true means are equal, we would conclude that the means are not equal, and we would accept the alternate hypothesis. Again, a remaining question is how do we decide that the true population variances are equal? And we're going to consider that later on with the F test. So in this screencast, we're considering the right side of this big flow chart. Are the variances known? If they're not known, then we have to ask ourselves, are the variances equal? If the variances are equal, then we ask ourselves, are the sample sizes equal? If not, then we're going to use a pooled sample variance or a pooled sample standard deviation, and our test statistic is this. If the sample sizes are equal and the variances are equal, our test statistic simplifies slightly. Now let's talk about the case when we can't assume that the 2 population variances are the same. So this is the variances unequal case. Our test statistic is a little bit different as shown here, and yet again this is usually equal to 0 because you're trying to just show if the means are equal or not. This follows the t-distribution with new degrees of freedom, and new is calculated using this big old complicated formula here. And the same procedure is used for hypothesis testing. We compare to T alpha with new degrees of freedom. So if the variances are not equal, if the sample sizes are equal, then our test statistic simplifies just a tiny bit, and we can use this equation to calculate our test statistic. By the way, an asterisk in both of these cases indicates that we have to use this complicated formula for degrees of freedom, and we're comparing to the t-distribution with new degrees of freedom, where the degrees of freedom are given here. So let's go through a couple examples. Here we have natural gas from 2 sources. Obviously we have different sample sizes. We have 7 versus 5. And we can also look at the sample standard deviations. Now for now, without knowing how to do the F test, we're just going to kind of make a quantitative judgment. These are relatively close, so we're going to assume that the 2 populations are the same. And we want to know, are the methane levels from the 2 sources equal? our sample data is suggesting that source 1 is greater than source 2, and so we're going to perform an upper-tailed test. Let's go ahead and do this in Excel. I've got this in a file called natural gas. Our test statistic, we have to use the pooled standard deviation, where the pooled standard deviation formula is shown down here. I've already named these things N1, N2, X bar 1, X bar 2, S1, S2. Let's go ahead then and calculate our test statistic. Our test statistic is given by this formula. We first need to calculate our pooled sample standard deviation, SP. So I've typed that formula in, verify that that's correct, and then press enter. So we're getting a pooled standard deviation of about 4.8. I'm going to go ahead and name this SP. And now we can calculate our test statistic. X bar 1 minus X bar 2 over SP divided by square root of 1 over N1 plus 1 over N2. Our test statistic is 1.78. We now need to compare to T alpha. This is an upper tailed test, T alpha, with N1 plus N2 minus 2 degrees of freedom. So this is simply T dot INV, 1 minus our alpha value. Degrees of freedom is N1 plus N2 minus 2 degrees of freedom. We always compare to the denominator degrees of freedom here. And when we press enter, we get a critical T alpha of 1.81. Since our test statistic does not exceed our critical T alpha, we can conclude that we reject the alternate. We could also real quick calculate a p-value. The p-value is just the area to the right of our test statistic. We can do that using the t.dis.rt function of our test statistic with n1 plus n2 minus 2 degrees of freedom, and that's about 0.052. So our p-value is not quite less than our alpha, and so we reject the alternate hypothesis.